Hello students, welcome you all. In my today's lecture, I will explain the analysis of 4+2 cycloaddition reaction by correlation diagram method. In my last lecture, I told you the analysis of 2+2 cycloaddition reaction by the correlation diagram method. So before going to this lecture, I will suggest you to go through my previous lecture. So that 2+2 cycloaddition reaction, that was an example of a 4n electron system. And now this 4+2 cycloaddition reaction, this is an example of 4n plus 2 electron system. 4n plus 2 electron system, or we may say that this is an example of 4n plus 2 pi electron system. Okay. Now, the simplest example for this 4+2 cycloaddition reaction is the Diels-Seder reaction. And when the butadiene, which is the diene system, that react with a dienophile, and here the dienophile is the ethene system. So these two pi system, they react either in presence of heat or it may react in presence of light to give the cyclohexene. So in cyclohexene, this is one of the new pi bond is formed and two new sigma bond is formed. These are the two new sigma bond which is formed in this reaction. Now in reactant and product, what are the molecular orbitals which are formed in this reactant and product? What are the molecular orbitals which are involved in the reaction in reactant and product? Now if you will see here, the molecular orbitals of butadiene and molecular orbitals of ethenes. In the same way, the molecular orbital of here, this pi system, molecular orbital of this sigma system, this is involved in the reaction. Now, the molecular orbitals of butadiene, we know 4 molecular orbitals of butadiene, and I may write psi1, psi2, psi3 and psi4. Whereas the molecular orbital of this pi, this will be pi 1, or we may write pi and pi star. In the same way, for here, for the cyclohexene, the molecular orbitals involved, this will be psi1 plus psi2, okay, and psi1 minus psi2. In the same way, psi1 star plus psi2 star, psi1 star minus psi2 star, and pi 1, this is the pi molecular orbital. I can write it because I have written here pi and pi star. So to distinguish this one with this one, and I will write here pi 1 and another one is pi 2 star. Okay. Now I may draw the correlation diagram for this 4+2 electron system. So for this, let's draw it. Okay, so 6 molecular orbitals in reactant and 6 molecular orbitals in product. So this is bonding, 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. So I may write the name. This may be written like this is psi1, this would be psi2, psi3, sorry. So, okay, so this would be psi1, and then I should write this pi. First psi1, then I have written pi, then psi2, then I should write this psi3, and then pi star and psi4. These are the 6 molecular orbitals that I have written for the reactant molecular orbital. So here I can write, these are the molecular orbital for this reactants, and this reacts either in presence of heat or in photochemical condition to give the cyclohexene. Now I should write the molecular orbitals for this product. So the product molecular orbitals that I should, or otherwise I should write it little below it. Suppose this is our butadiene system, this react with ethene system, and either heat or photochemical condition. Now this product molecular orbitals, so they should be written like this. So these are the two product molecular orbitals, and these two molecular orbitals I have written the energy of these two molecular orbitals. This is less than this psi 1. So why, I will tell you. So this is our sigma 1 plus sigma 2, and this is sigma 1 plus sigma 2. This will be sigma 1 minus sigma 2. Now next one that I will write, this is pi 1. So I will write the pi 1 just above this pi. This is our pi 1, and next I should write this one. Then I should write the next orbital here. Okay, so this is pi 1 star, and then I should write sigma 1 plus sigma 2, sigma 1 plus sigma 1 star plus sigma 2 star, and above the sigma 1 star plus sigma 2 star I have written above psi 4, and then this one sigma 1 star minus sigma 2 star. Okay, so these two orbitals, these two molecular orbitals, the energy of these two molecular orbitals is more than that of this psi 4. Now why this energy level I have drawn such energy levels, but why the difference of this energy level? So I will tell you why I have drawn in this way. So this can be understood. Suppose if I have written this psi 1. Now what is this psi 1? Okay, so this is psi 1 where all lobes this have the positive sign. Upper lobe we may write this negative, 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 negative. What about this pi? Pi, this may write as this both positive, and psi 2, if I want to write the psi 2 of this butadiene, then we know that 2 positive lobe and 2 negative lobe, like this we can write for psi 2. So the molecular orbital diagram for this butadiene and other system I have already covered in my previous lectures, so you may see that one. And then about this psi 3 of this butadiene, because it is having the 2 node, one node I may draw here, another node I may draw here. So this is our plus, and this is also plus, minus, minus. Now pi star, because this is pi and pi star, so this upper lobe sign we can write the upper lobe sign just opposite of this lower lobe sign, so we may write the upper lobe sign. Okay, so this is pi star, here this is plus, this is minus. In the same way we can write for this one, psi 4, means one is positive and it is negative, then again positive, again negative. Okay, now so if we see the why this psi 1 is below this pi, why pi is below psi 2, we may understood with the help of bonding interaction and the anti-bonding interaction between the orbitals. So if you will see here, then total number of bonding orbital, this is one bonding interaction, this is another bonding interactions, and these three bonding interactions are there between these orbitals. Whereas in pi system we have only one bonding interaction. So three bonding interaction and one bonding interaction, and bonding being the more stable, so that's why psi1 is below pi. In the same way, we may compare the energy levels of this pi and psi2. So this pi is having one bonding interaction, whereas psi2 is having two bonding interaction. This is plus plus and minus minus, and it is also having one anti-bonding interaction over here, plus and minus. It is also having one anti-bonding interaction. So two bonding interaction, and one anti-bonding interaction. So overall you will get the one bonding interaction. But because here one bonding interaction, here also you will have one bonding interaction. So but the energy of this pi is less than that of this psi2, because one of the anti-bonding interaction is present in these molecular orbital, So that's why pi is below this psi2. In the same way, with the help of bonding interaction and anti-bonding interaction, we may decide the energy levels of these molecular orbitals. Now if you will see this psi3 and pi star, if you want to compare this psi3 and pi star, then total number of bonding interaction, if you will see, one bonding interaction, whereas total number of anti-bonding interaction, one anti-bonding interaction, two anti-bonding interaction. So two anti-bonding interaction is there, two anti-bonding interaction and one bonding interaction. So overall it is having one anti-bonding interaction, and whereas here you will see one anti-bonding interaction. Okay, but the energy of this psi3 is lower than that of pi star. Why? Because it is having one bonding interaction, whereas there is no bonding interaction present in this pi molecular orbital, pi star molecular orbital. In the same way here, the total number of anti-bonding interaction is three anti-bonding interaction. That's why here one anti-bonding interaction. That's why it is having the lower energy. This is having the higher energy. Now let's see the energy, this molecular orbitals for this this product molecular orbitals. So this is sigma 1 plus sigma 2 and sigma 1 minus 2. So no doubt this sigma molecular orbitals. So I have drawn this sigma molecular orbitals below this pi molecular orbitals. The sigma molecular orbitals will always having the or sigma bonding molecular orbitals. These are the sigma bonding molecular orbitals, whereas these are the sigma anti-bonding molecular orbitals. And the sigma bonding molecular orbitals will always being the more stable, having the less energy in comparison to this pi molecular orbitals. So that's why both these molecular orbitals is having the lower energy in comparison to these pi molecular orbitals. Now if you want to see how we can draw this psi1 plus psi2, then okay, so this is plus 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 and plus. So this is our sigma 1 and this is sigma 2. So sigma 1 plus sigma 2, okay, sigma 1 plus sigma 2, and if you want to draw one of this pi bond over here, then we may draw pi bond. Whereas if we want to draw this one, then this may be drawn. So this is sigma 1, this is our sigma 1 plus plus, whereas minus minus, because we have just opposite sign of this sigma 2, because this is minus sigma 2, and we have to reverse this sign. If we have plus plus over here, then we will have minus minus over here. So this is sigma 1, this is sigma 2. Then about this pi 1, if we see this pi 1, and this would be our pi 1 plus plus. Okay. Now, so this pi 1, no doubt, this if we compare this pi 1 with this sigma 1 minus sigma 2, here you may see two bonding interaction, this one and this one, whereas here we may see only one bonding interaction. That's why this molecular orbital being the more stable orbital in comparison to this one, so that's why it is above and this is below. In the same way we may write for this one. So pi 1 star, so if this is pi 1, then pi 1 star is, this is plus and this is minus. We may give the sign for this upper lobe, and this would be just opposite of this lower lobe. Now what about this sigma 1 star plus sigma 2 star? So on the same basis we may write sigma 1 star plus sigma 2 star. Okay, so if sigma 1 star, if you want to write the sigma 1 star, then 1 plus sign, another lobe will having the minus sign, and sigma 2 star, that is again plus and minus. So this is sigma 1 star plus sigma 2 star. Now if you want to write the sigma 1 star minus sigma 2 star, so this is plus minus, this is sigma 1 star, and this will be having sigma 2 star minus plus sigma 2 star. Okay, so these are some molecular orbitals for this one. And now if you will see how we can correlate this one, if you want to correlate this one, then how we can correlate these molecular orbitals. So for this we should write the symmetries. For this we should write the symmetries of these molecular orbitals. Now in my last lecture of 2 plus 2 cycloaddition reactions, in 2 plus 2 cycloaddition reaction, when I took the example of 2 ethene system, when it was giving the cyclobutane, then the symmetries which were present, that were the mirror plane symmetry, which is the one of the mirror plane symmetries, vertical mirror plane symmetry, and another was the horizontal mirror plane symmetry. But here, so usually in pericyclic reaction we talk about two type of symmetry. One is the mirror plane symmetry, another one is the this C2 symmetry, or rotation axis. We see the rotation axis, like in electrocyclic reaction, and the symmetry where that we talk about, that were the two symmetries. One was the mirror plane symmetry, another was the C2 symmetry. And but here no C2 symmetry is involved in either in reactant and product. If you see, no C2 symmetry is there. If I draw one of the rotation axis over here, then we will not after rotating it by any either 180-degree angle or any angle, we will not get the same reactants. In the same way, we will not get the this one. So C2 is not present in reactants and product. Okay, so what is present here? If I draw one of the mirror plane like this, and if this mirror plane is a vertical mirror plane, then this vertical mirror plane, it divides this reactant into two equal half. So this is our vertical mirror plane. And if I draw the one of the horizontal mirror plane, then that will not divide this reactant into two equal half. So that's why only the vertical mirror plane symmetry is present in the reactant. And if you see the product also, so in product also you will find only a vertical mirror plane. And if I draw one of the horizontal mirror plane over here, then this will not have any horizontal mirror plane. So here we should only check the vertical mirror plane in reactant orbitals and the product orbitals. So now let's see, in this psi1, which either this is symmetrical with respect to the vertical mirror plane or not. Yes, this is symmetrical with respect to the vertical mirror plane, because this divides this in a same half, and that's why it is having the vertical mirror plane. That is, we can say this is symmetric with respect to the vertical mirror plane. Now what about this pi? If I draw one of the mirror plane over here, then this also divides this pi molecular orbital into the same half, so that's why it is also having this vertical mirror plane. Now I draw one of the vertical mirror plane over here. This is not dividing this into two same half, because this is plus, and in front of plus you are having minus, in front of plus you are having minus. That's why we can say this is anti-symmetric with respect to this vertical mirror plane. Now what about this psi3? Now in front of minus you are having minus, in front of plus you are having plus, and it divides this molecular orbital into the same half. So this is also having the symmetrical vertical mirror plane. And here what about this pi star? So in front of plus you are having minus, that's why it is anti-symmetric. What about this one? Here minus, this is having plus, here plus, it is having minus, that's why it is also anti-symmetric with respect to the mirror plane. Now in product molecular orbital, in the same way we may check for the product molecular orbital. Now if I draw one of the mirror plane, vertical mirror plane over here, and what you will find, in front of plus we are having plus in front. Okay, so it is dividing, and this mirror plane is dividing into two same half, so that's why it is having the symmetrical. It is symmetric with respect to the sigma v. And here if we see, then in front of plus minus, that's why it is anti-symmetric with respect to the sigma v. What about this? This is also symmetric with respect to the sigma v. What about this? This is anti-symmetric. In front of plus we have minus, it is not dividing into same half, so that's why it is anti-symmetric. And this one, in front of plus, in front of minus, same half, two same half, that's why it is symmetric. And what about this? In front of plus we have minus, in minus we have plus, so it is anti-symmetric with respect to sigma v. Okay, so we have written the symmetries of these molecular orbitals. Now in correlation diagram, what we do, the molecular orbitals having the same symmetries, molecular orbitals in reactant and product which have the same symmetries are joined with the help of a straight line. So we should see the molecular orbitals of the reactant having the same symmetry in product. So this psi1 is symmetric with respect to sigma v, and here the symmetric molecular orbital, this is one of the symmetric molecular orbitals, this is symmetric, this is symmetric. So out of this three symmetric molecular orbital, this sigma 1 plus sigma 2 is having the lowest energy. That's why I should join it by this straight line. Now this symmetric, that may be joined here like this, and this anti-symmetric should be joined with anti-symmetric. Here if you will see in product we have 1, 2, 3 anti-symmetric molecular orbital, but this is having the lowest energy, that's why I should join with here. Now this psi3 having the symmetric with respect to sigma v, so that should be joined with the symmetric molecular orbital, and only symmetric molecular orbital left is this one. So sigma 1 star plus sigma 2 star is the only symmetric molecular orbital. Now this one anti-symmetric, pi star is anti-symmetric, and I should join it with this pi star, and then this should be joined with this one. This is only left anti-symmetric like this. So you may see this is the correlation diagram for the 4+2 cycloaddition reaction. And now if you see the energy difference between this pi and pi star, So I have drawn the energy level of this pi is a little higher than that of pi 1, because these molecular orbital, this pi molecular orbital is under the influence of this butadiene pi molecular orbitals. So this gives it a low energy, whereas this pi system is not under the influence of any other pi bond. So this is under the influence of other pi bonds in butadiene. So that's why it is having the lower, having the lower energy. Sorry, this should, okay, this should having the lower energy, slightly lower energy. This should be having slightly lower energy. I should draw this one slightly lower in comparison to this one. I should draw slightly lower in comparison to this one. I should draw here. Okay, now this one can be correlated like this. So it is having lower, no. So I should draw somewhere lower than this. So now like this. Okay. So this should be the energy level of here and opposite to here. So this should go to the higher energy in comparison to this, because this is the here anti-bonding interaction is going on. So this is the correct diagram for this 4+2 cycloaddition reaction. Now whether we should check for this whether this is thermally allowed or which is photochemically allowed. So for this, because this is a 4n+2 electron system having 6 electrons, this is having the 6 electrons. So as it is having the 6 electrons, so under thermal condition, if you will see under thermal condition, 6 electrons which are present in the ground state. These are the 6 electrons which are present in the ground state under thermal condition. And in psi1, if you will see, in psi1, 2 electrons are present. In psi2, here this is the psi2, here sorry, this is our pi, this is our pi1, pi. So, and psi1 is going into this. Now for simplicity, I may write this one as, suppose I write it as A, this may be written as B, this I am writing as a C for simplicity, and this I should write it as a D, suppose. So this is A, B and C, D. Now this psi1 electrons, these are going into this sigma 1 plus sigma 2 or this A. So 2 electrons I should write like this. Okay, 2 electrons I have written this one. Then this pi electrons, then this pi, 2 electrons of this pi, okay, 2 electrons of this pi. So they are going into this pi 1, and 2 electrons inside 2, they are going into this B, that is sigma 1 minus sigma 2. So like this. Now, so if you see, this is the ground state and this is also the ground state molecular orbitals. These molecular orbitals in reactant, these are ground state molecular orbitals. In product, these are also the ground state molecular orbitals. So this the transfer of this electron from this ground state to this ground state, this is energetically favorable. So that's why this is favored. Okay. So 4+2 electron system, this is favored. This is favored under this thermal condition. Now, if you will see under photochemical condition, one of the electron from here that would be excited to the higher energy level. Suppose it goes here. Okay. Then what should I see? You may write. This psi1 electron is having this psi1 molecular orbital having the 2 electrons, and this pi is having 2 electrons, psi2 is having 1 electron, and psi3 is having 1 electron. Now this psi1 electrons, it is transferred to here A molecular orbital, whereas pi is going into pi1 and psi2 electrons into B and psi3 electron into C. Okay, so if you will see here, then this is our first ground state, this is first ground state, this is second ground state, and this may be called as the higher energy state or the third, this is first excited state, this is second excited state, and this higher energy excited state that we may write. So this is first excited state, whereas this is first excited state, and this is the higher energy excited state or second excited state. So here the electron from this is psi3, this is transferred to this higher energy excited state, from, we can say, from first excited state to the higher energy excited state. So here these correspond to this first excited state, whereas these molecular orbitals, they correspond to the higher energy excited state. So this the transfer of this electron, this is energetically, this is not favorable, so that's why this is disallowed. So this is disfavored, whereas that one is favored one. So but we can write the selection rule. But we can write the selection rule for this 4 plus 2 cycloaddition reaction. So for 4n electron system and for 4n plus 2 electron system, okay, under thermal condition, what we saw in my previous lecture, for 4n electron system, this was disallowed under thermal condition and allowed under the photochemical condition. Whereas if you see this 4n electron system, for 4n plus 2 electron system, under thermal condition it is favored, whereas under photochemical condition it is disfavored. So this is the selection rule for this 4 plus 2 cycloaddition reaction, or the selection rule for the this cycloaddition reaction that we have seen by the correlation diagram method. Now in my next lecture I will analyze this cycloaddition reaction by frontier molecular orbital method. Thank you.